Hello everyone, welcome back to my channel. My name is Mohit and in this video we will see how graph convolution network works. So let's get started. So basically, why do we need graph convolution network when we already have recurrent neural network and convolutional network? So basically, in normal neural networks, we see that we usually make use of a grid for the data structure. Like we have a data in the form of a grid, right, where we have some uh, rows and columns, and images are usually in the form of grids, whereas we see that the text is usually in the form of the sequence like a b c etc. Okay, but for the graphs where we have nodes and edges, we don't have a particular format to analyze graphs using neural networks. Okay, so because in graphs there is no ordering and no definite structure, so that is why we need graph convolution networks. And in many real world use cases like social network, right, or maybe in molecules, or maybe in research like citations, the graph is heavily used. Okay, so now let us consider an example, and based on that example we will see how it works. So let us consider a Cora citation data set. Okay, which, I mean, it is a classical data set which is heavily used to analyze the graph convolution network. Now in this data set we have around 2708 papers, right? So it means we have 2708 nodes. Okay, each paper is a node, and in this data set each node is described by 1433 features. So the features per node are 1433. Okay, this could be any features like based upon the location, the title, abstract, length of the paper, journal, etc. Now we also have edges. Okay, so there are around 10,556 citations. So citations are somewhat which linked one paper with another paper, like there is one paper which is cited by another paper, right, or this paper is also cited by this paper, vice versa. So there are around 10,556 citations, and there are 7 categories. Okay, so it means that there are 7 categories of research papers, right? So this means that this data set has a feature vector of 1433, because this is the number of features that it has, and the labels are between 1 to 7. Okay, so these are the labels. Now what is our goal? Our goal is to classify these papers using both their content and their citation structure. Okay, so if we want to analyze this particular data set, then what we will do, we will create a neural network layer which particularly follows this structure, which is h of layer L plus 1 is equal to some sigmoid D minus half A D minus half H L W L. So this is quite complicated formula that we generally use for our graph convolution networks. So in this formula, what is H? So H is basically the node features at layer L plus 1. Similarly, this one is for layer L. Okay. A is our adjacency matrix. Okay. And D is our degree matrix. Right. W is our trainable weights. Okay. And yeah, sigma is some non-linearity. So you can see that now if you want to analyze this particular data set, or if you want to perform the classification task, we have to utilize this particular formula for our neural network. Now for these many number of nodes and for this number of features, it is quite difficult and challenging as well to uh, implement it from the scratch and see how it works. So in order to do that, we will pick up a simpler example. Okay. So let us say we have three nodes 0, 1, 2. Okay. So 1 is connected with 0 and 2. Okay. Now first we have to check whether what is the adjacency matrix between this particular graph. Okay. This is a graph. So the adjacency matrix can be written as this, because it is we have three nodes, so it will be a 3 by 3 matrix. Okay. So 0 node is only connected with node 1. Okay. 1 node is connected with 0 and 2, and 2 is only connected with 1, right? So this is for 0th row, right? So 0 is connected with 1, so it is 1, we will put 1 here. It is not connected with 2, so we will put 0 here. Now for 1, it is connected with 0, we will put 0 here, we will put 1 here, and 1 is also connected with 2, we will put 2 here, right? And 2 is only connected with 1, so it means we will put 1 here, and rest of other cells are 0, right? So now we have built the urgency matrix out of this graph. Now the second step is that the nodes are not connected with each other. Okay. So in order to connect them with themselves, we will add self loops. So it can be represented like this, like 0 is connected with 0, 1 is connected with 1, 2 is connected with 2. So how we will do that? We will define another urgency matrix, which is a hat, which is equal to a plus I. Okay. We will add identity matrix to matrix A. Now this A matrix will be what? 0 1 0 1 0 1 0 1 0 plus 1 0 0 0 1 0 0 0 1. Okay. So it will be 1 1 0 1 1 1 0 1 1. Okay. So now each node is also connected with itself, and we have formed this redefined urgency matrix. Okay. Which will tell us which node is connected to which another node. Now once we have connected, we have built this matrix, the next step is to create the degree matrix. Now how we will do this? Degree matrix will basically tell us that with how many nodes a particular node is connected. Okay. So we have seen that node 0 is connected with two nodes based on our A matrix, which is 1 1 0 1 1 1 0 1 1. Okay, so node 0 is connected with two other nodes. Okay, node 1 is connected with three nodes, and node 2 is connected with two nodes. Okay, so degree matrix is the diagonal matrix. Okay, so it can be represented as 2 3 2. Okay, rest are 0. Okay, so now we have constructed two quantities, a hat and d hat. Okay, now since in that formula we had d hat, sorry, d minus half. Okay, so I'm using different notation. I'm using hat here. So our d hat minus half can be computed from D matrix like this. So basically we just have to take the inverse and take the square root. So the first element would be 1 by root 2 0 0, then 1 by root 3 0, and then 1 by root 2. Okay, so this can be represented as 1 by root 2 is simply 0.707 00, and 1 by root 3 is 0.517, and similarly 1 by root 2 is also 0.707. Okay, so now we have created our d hat inverse, square root of d hat inverse. Okay, now if you see, we have to compute this quantity first. Okay, so let's compute it. So basically let's give it a name, which is s. So it is d hat minus half a hat d hat half, sorry, minus half. Okay, now we can also compute it element wise, like Sij would be a hat ij divided by root di hat dj hat. Because this is just a matrix, so we can also compute elements of this matrix, and then we will combine it. So what would be our S00 term? So S00 would be a hat 00 divided by root d hat 0 d hat 0. Okay, so a hat 00 is 1. Okay, this one. So it is 1 by, and what is the d is a dimension with how many nodes it is connected. So it is connected with two nodes. So 2 by 2, it is 1 by 2, which is 0.5. Similarly for S01, we will have a hat is 1. So 1 divided by, it is connected with 2 and 3. So 2 multiplied by 3, which is 1 by root 6. Okay, so it is nothing but 0.408. Now for S11, we will have 1 divided by 3 multiplied by 3, which is 1 by 3 or 0.33. Okay, similarly for S12, we have 1 divided by 3 multiplied by 2, which is 1 by root 6. So it is also 0.408. And lastly we have S22, which is 1 by 2. Okay, which is nothing but 0.5. So we have constructed all the elements of S matrix. So the S matrix can be represented as 0.5 and this 0.408 this one is 0, and similarly S10 is 0.408, S11 is 0.33, S12 is 0.408. Okay, so this one is also 0. Then S21 is also 0.408, and S22 is 0.5. Okay, so now we have constructed this quantity. Okay, so now we need H matrix and W matrix. Okay, so H matrix, as we have seen earlier, it defines the node features. So every node can be represented as a number of features. So let us say that it is uh, given by two features only. Like for node 0 we have some numbers 1 2, and for node 1 we have 3 4, for node 2 we have 5 6. So this is for node 0, this is for node 1, and this is for node 2. Okay, and similarly for the weight matrix, we can initialize weight matrix randomly in our neural network, but let's say it is given by this 1001 for simplicity, because we have only two features. Okay, so now our task is now become very simple, that so this H matrix is usually given to us. For in this case it is 2708 by 114 1433, and W matrix is 1433 times 1433, because it is a weight matrix. And simply you can also compute this urgency matrix, which is S, for this particular Cora citation data set. Okay, so now one thing we didn't mention, that we already have urgency matrix A or A hat, right? Then why do we need to multiply it with d hat minus half and d hat half? So basically we could also do it simply. We can also multiply A with H and W, but we need to do this thing. This is because if one node is connected with too many neighbors, like say you have one node which is connected with 100 another nodes. Okay, so and other nodes, let's say node 2 is connected with only 3 nodes. So this imbalance creates, I mean, it will create new features which will either blow up, okay, or will either shrink. So to make it not happen, we will generally try to balance the this quantity by adding the urgency matrix with this degree matrix. So basically we will try to normalize it, the urgency matrix, so that uh, if a node has a, let's say, 100 neighbors, so its features will not blow up. Okay, so this normalization technique, I mean, makes it makes the contribution balanced. Okay, so I hope you like this video, and see you in the next video. Thanks.